and do the simple batch script examples. And these are all in the exercises simple section that you found after either cloning or downloading the exercises. And here will be some serial examples, MPI examples, and GPU examples. And there are some examples of how to use constraints for specific CPUs and GPUs. Now, all these exercises should be run from either a terminal in a regular SSH session or from inside ThinLink in an SSH window you open there, not from Open on Demand, because they will already be running in the batch system there. So. For consistency and to make it easier for you to find things in this directory, I have given all the example batch scripts the suffix .sh, even though not required. As I said, you could also call them .batch or .sbatch or nothing whatsoever. It's your choice. In order to run programs mentioned in the batch script, you need to compile them, except for the compile run.sh and the CUDA examples, which includes compilation. Remember again, the course project has the following project ID, HPC2N 2026-002. All the examples in this directory should have the correct project added. If you are not in this project, or if you want to run it in your own project, you need to change it in the submit scripts. Otherwise, you can just run them. And to add a project to a submit script, you would use this line here, where you replace this if you're using a different one. It's already added to all of them. The storage project, you are already working in that, so there's nothing that needs to be done here. If you want to, you could try and make changes to the C programs. You could try rewrite or add different programs, change number of cores and GPUs. In general, play around with the examples. I would suggest using the FOSS compiler toolchain version 2023b. There isn't any specific reason other than it's available on both the Intel and AMD nodes, and it has CUDA that will work with it also. If you decide to use a different one, and you can, you will have to make changes to some of the batch scripts. Remember, submit with sbatch and the name you gave your job script. In most of these examples, I have named the executable that I compiled with the flag -O. I am not very inventive. I'm just naming it so the same as the C program, just without .c. So if it was called mpi_greeting.c, the executable is mpi_greeting. If you're using the same naming style, you won't need to make changes to any of the submit scripts. If you don't include a name, if you name it something else, you have to make changes. So let's go ahead and look at these examples. We have first one that is hello.sh. I'm going to open it. And it looks this way. And you can see here that it's a serial program. It's asking for 1 core, 1 minute, and it has the course project. In addition, I'm using FOSS 2023b. And then there's a thing to look for. What is the name of the executable? It's hello. Let's try exit and see if there is something named hello here. I'll just remove some of these scripts to get fewer files. I do indeed have hello.c, and I used it earlier, but let's go ahead and compile it again. GCC hello.c minus O. Wait, let us first check that we actually have loaded a module. We haven't, so we can't compile anything. So module load FOSS 2023B. And now it's loaded. Good. So now we say GCC hello.c minus O hello. We now have the program hello compiled. It's an executable here. And let's go ahead and submit it. Sbatch hello.sh. It's a very short program. It's running already, and it will soon have ran. So this one you should test. MPI batch job should test that as well. You need MPI underscore hello.c. Compile it. MPI cc. MPI underscore hello.c minus O, like this. And then submit MPI hello sh. You can try and rerun it. You can try ask for more cores if you want to. And you will see that the output will be random. Here I asked for 14 cores. That should be enough. So I run it again. It has run once. And I got this output here. Let's see if it has run again. It has run again. Good. Let's just throw the output to the screen so we can see that it's probably going to be random. It is random, but it's... So you can see the order they run in is random. The MPI, OpenMP, sorry, batch job. Let's compile that. GCC minus F OpenMP OMP hello C minus O OMP hello. And then we submit it. I believe this is the name of it, yes. And here you can, inside of it, make changes. You can, I have just set it to export the number of threads that that is the number of core you asked for, but you can change that. And you shouldn't set it to more cores, to more tasks than the number of cores. There is a number of other programs here. There's multiple serial jobs from the same submit file. It shows how, or rather one way of running several programs inside the same submit file. You need to compile these 4 scripts, 4 C programs, exactly the same way. Hello C is already compiled. The others you compile with GCC and the name of it, and then give them a name, the output name. And there is a job arrays. Job arrays is a mechanism for submitting and managing collections of similar jobs. All jobs must have the same initial options, size, time limit, etc., but you can change some of them after it has started execution. I have a small Python script that's called hello world minus array.py and a batch script hello world array.sh that you can use to try and submit with job arrays. When you submit that, you will get output from each of these arrays. And in this case, there is 10 tasks in the array. So if I say sbatch hello world array, then it should give me output for each of these. And you can see here that the outputs will be called hello world, the job ID, and the array number. So let's see if it has done any of those. Indeed, it has. It has run all of them here. So that would look like this. You can name them differently, of course, but the percentage J is the job ID. Percentage A is the number task in the array. So you can play with that. And you can also run parallel jobs sequentially. The thing here is you simply run them one at a time. And that means that you just need enough cores that the largest of them can run because they run one after another. So you need also enough time that they will all complete. If you want to run them simultaneously instead, then you need to ask for enough cores that all of them can run at the same time and for all of them to complete, of course. Another thing to pay attention to is that when you're running simultaneously, you have to add an ampersand after and a wait. If you don't do this, if you don't add the wait, then it will just end the job as soon as the first of them finishes. It needs the wait to wait for all of them to finish. And of course, also you can compile and run inside of a batch job. It's not something that's usually a good idea, but maybe you will actually have to run on a different type of node than the one that you submit from. And in that case, maybe you need to run it in order to get it, you need to compile it in order to get it for that architecture. So doing that, you simply load the modules and then compile it and run it. As I mentioned earlier, you can split errors and outputs. You do that with these commands here. Minus minus error equals something, minus minus output equals something. Name them as you want to. Percentage GA in it assures you that they will create that a new one will be created for each run of the job instead of overwriting it. Dependencies. Not going to go into this hugely, but maybe you have a pipeline where jobs depend on a previous job. You can handle it through Slurm, with, where you submit one job and you then tell Slurm to wait for that job to finish before it starts the next job. And that would be done with -d after OK and the job ID of the previous one that you got here. And it's actually possible to make a script to take the job ID from the first job, even if not known yet, and use it as a prerequisite for the next job. And that's done like this. So this way you can set up a chain of jobs where they should not run until after the previous one has finished. CUDA GPU programs. You need to allocate GPUs in the job script. They are not allocated by your program. I have seen this many times. People are trying to run a GPU script and they are using GPUs, they think, but they are not asking for them, so then they will not get any allocated. You need to allocate them the way that I just mentioned. So ask for the number of GPUs or the GPU cards, say which ones you want if you have constraints. If it is something that is running an actual CUDA, then you regularly would need to load CUDA. This is the newest CUDA that's on all of the nodes right now. And here are some examples where you can ask for a V100, for a A100, and so on. So there are just examples here. Since the project has L40Ss, I think you should just use that example and only ask for that, because I'm not sure you're actually going to be able to get any of the other GPUs with this project, because it's currently locked to the reservation. So after 5 o'clock today, you can test for other types of GPUs than the L40Ss, because you will be able to use this project for another week or so, at least until 1st February. By then, you will not be able to use the project anymore because we need it for a different course. But you can use it until the 1st of February. After that, you should also save any data you want to keep in the project storage, because we may need it for the other course. But generally, you can use the projects 1-2 weeks after courses to test things in. There are examples here for different types of GPU features, how you can ask for those. So that's something to test for as well. But there are several exercises here, and also it's possible to run Jupyter Lab from inside ThinLink if you want to do that. Otherwise, try it through the Open On Demand desktop. There is a lot of examples here, and you don't need to do all of them, but try to do at least one serial, one MPI, and 1 or 2 GPUs, and also test the Open On Demand system or the ThinLink. Let's take until 1405 and do exercises.